This is 4.5b. Yeah. So, you guys are aware that there are an infinite number of ways to write the fraction 1/2. 1/2, 2/4, 13/26, lots and lots of ways. So, in mathematics, we have sort of mandated that anytime you have a fraction, you need to check to see if it can be simplified, and if it does, simplify it as far as it will go. That's just one of the rules. Square roots have simplification rules as well. And while they're not quite as obvious, they are just as useful as, in fact, more useful than simplifying fractions. So one of the rules is when we have a square root, we check to see if we can take anything from the inside and place it on the outside. That's what we've been working on lately. Another rule is we never leave a radical, a root of any size, in the denominator of a fraction. Now, a lot of the times when you rationalize a fraction or rationalize the denominator, the end result will appear more complicated than the original. But that's just the rule we have decided upon. And a lot of times it makes it more simple. But every once in a while, the answer is going to look more complicated than the original. So here, I have 8 over the square root of 5. I want that radical, that root, out of the denominator. So the method of rationalizing the denominator is figuring out some number that I can multiply to the square root of 5 and end up with a result that is not a square root. Multiply it by itself. So times the bottom by root 5. Is that going to affect the size of the original number, the original fraction? Yeah. If I multiply both the top and the bottom by the square root of 5, does that change the size of the original fraction? No. Why not? Why can I multiply by root 5 over root 5 and not affect the original number? It's just 1. Root 5 over root 5 is just a fancy way to write the number 1, and multiplying by 1 has no effect. The top becomes 8 root 5, and the bottom becomes the square root of 5 times the square root of 5. How do we multiply roots? Well, you do outside times outside and inside times inside. The outsides are both 1s, so 1 times 1 is 1, and then insides are both root 5, so I get root 25, and 1 root 25 is just 5. Another way to look at it is the square root of 5 squared. The squared and the square root cancel each other, and I just get 5. And remember that the square root is really just the 1/2 power. So this is 5 to the 1/2 to the second. And how do we raise an exponent to an exponent? We multiply. If I had x squared to the third, that would just be 3 copies of x squared, which is x to the 6th. Now, that is different than this. X to the 2 to the third. What is that? Well, in this case, I am cubing the x squared. What's happening here? I'm just cubing the 2. So this would be x to the 8 because it's sort of like that. So when we have a base to an exponent raised to an exponent, we just multiply these. And what is 1/2 times 2? It's just 5. So lots of different ways to show that the square root of 5 times the square root of 5 is 5. When I get here, now I need to check, can I simplify anything there? Well, nothing on the inside of a root can be simplified, canceled, with anything outside of a root. So these are not simplifiable. And then we check those. 8 and 5 have no common factors, so there's nothing we can do. Okay. Here we multiply. So I have a binomial times a binomial. So multiply that. Outside times outside, inside times inside. This is a 1. 2 times 1 is 2. Root 6 times root 10 is root 60. Now that. Outside times outside is negative 10. And inside times inside would be root 6. Does everybody get that? Okay. This one, outside times outside, negative 5, inside times inside, root 10. And this is plus 25. Okay. Are any of the terms like terms? No. They all have different radicals, or none at all. But I need to check to see if any of those terms simplify. 60 is 6, 10, 2, 3, 2, 5. Can I bring anything out? Set of 2's. And that comes out here and gets multiplied. So 4 root, what's left over? 15. 6 is just 2 times 3. 10 is just 2 times 5. So nothing else simplifies. So minus 10 root 6 minus 5 root 10 plus 25. That is the simplified version. Okay, good. Okay. Here, none of my roots are the same. 45 is 3 times 3 times 5. And this is 2 times 2 times 5. Bring out a 3. That becomes 6 root 5 plus 15 root 5 minus 2 root 5. Now all of my radicals have the same value. 6 plus 15 is 21, minus 2 is 19 root 5. All right. 63 is 3 times 3 times 7. 28 is 2 times 2 times 7. Bring those out. 3 root 7z minus 2 root 7z. 3 minus 2 is just 1 root 7z. Okay. We need to rationalize the denominator. So I times it by the square root of 3 over the square root of 3. On top, the outsides are both 1. The inside becomes 15, or root 15w. And the bottom becomes 3. Can I pull a 3 out of those? No. Inside and outside cannot cancel because it's not really a 15. Right? The inside is not really a 3 and a 5. It's the square root of 3 and the square root of 5. Does the square root of 3 cancel the 3? No, it doesn't. So insides cannot You cannot cancel factors from an inside and an outside. All right. So here the outsides are both 1. So I get the square root of 20y to the 7th. Factor that down. 2 times 2 times 5, and then 7 y's. Pull out a 2. How many y's can I bring out? Bring out 6. What does it become on the outside? A 3. 2y to the 3rd. And that leaves me with a 5 and a y on the inside. Okay. Okay. This is tricky. Okay. I have a radical in the denominator, but I also have a constant, or I actually have 2 radicals in the denominator in this case. Okay. So if I times the bottom by root 11, is that going to get rid of all of my radicals in the denominator? No, it'll get rid of one of them. So I would get root 11 squared minus root 55. And this would go away. Is he on his phone again? Oh, you really need to quit that. I get 11 minus the square root of 55. And that was good. I got rid of one of them. How do I get rid of the other one? Well, what if I times it by root 55? Is that going to work? That will get rid of this one, but then it will create a root again on the other side. Close. Yes. Do you remember when we started doing stuff like this? What do we call these? So they're binomials, and they have a special name because they have the same values with a different sign in the middle. They're called conjugates. And conjugates are really nice to multiply together because you get this. And the middle two cancel. We get x squared minus 16. Okay? This has a special name. Difference of perfect squares. Right? Anytime you multiply conjugates together, you get a difference of perfect squares. That middle term is going to cancel. Okay? And notice, this is just x squared, and this is just 4 squared, which is going to be really handy in this case, because over here, if I square the root 11, then the radical goes away. If I square the root 5, then the radical goes away. But what about the stuff in the middle? It will cancel as long as I use a conjugate. So I'm going to multiply by the square root of 11 plus the square root of 5. Did I choose that because that's the numerator? No. I chose it because it is the conjugate of the denominator. Okay? And in order to not affect the value of the original fraction, I have to do the same thing to the top. The top is a little bit difficult. What is root 11 times root 11? 11. Okay. What is root 11 times root 5? Root 55. And 5 times root 11? Also root 55. And root 5 times root 5? 5. So root 55 is 11 and 5. That's not going to simplify. But the numerator becomes 6 plus 2 root 55. Not 6, 16. Everybody understand that? Okay. Now the bottom. I have 2 of these. What is that? 11. What is that? Root 55. Okay. What is this? Negative root 55. And what is this? Negative 5. It's negative root 25, which simplifies down to be negative 5. And the middle drops out. The first and last terms no longer have a radical in them. So we just subtract them together and we get 6. And we have just rationalized the denominator. Now, which one is more simple? I guess you could kind of debate it, but we prefer this method. Oh, good job. Can this go any farther? Yeah. It was 11 minus 5. Because it was, so it was, you do flip the bottom, but that gives me 11, and this gives me 5, negative 5. Remember, it's x squared minus 16. Would x squared plus 16 work? Is that factorable? X plus 4 and x plus 4. Is that right? No. Is 4 plus 4 0? No. So I have to make one of them negative. Does that work? No. Is negative 4 times positive 4 negative 16? Or positive 16? No. So what if I make them both negative? Now it doesn't equal 0 again. So this does not factor into any real situation. You would need i's. So that's why it's a difference of perfect squares. The last term has to be negative. Oh boy. Okay. Do these have anything in common? They all have a 2. So we take a 2 out of everything and we get 8 plus root 55 over 3. Okay. All right. How do we do this? Well, I'm going to split it into the 4th root of 5 over the 4th root of 27. Okay. How do we, actually, I don't want to do this one yet. Let's do 3rd root first, and then we'll do a 4th root problem. How do I rationalize the bottom? I need 3 root 27s, and we better not do 27, because that actually, the 3rd root of 27 exists. So let's say 4. So if I multiply by the 3rd root of 4, is that going to cancel the radical? No, I need 3 of them. I need it to be the 3rd root of 4 to the 3rd. If I raise this to the 2nd, that doesn't really help. So 3rd root of 4 times the 3rd root of 4. So on top, I have the 3rd root of 4 times the 3rd root of 4. The bottom is the 3rd root of 4 to the 3rd, so that cancels. So I get 4. And then on top, I get 20 times 4 is 80, the 3rd root of 80. Does 80 simplify? Well, 80 is made up of 5, 4, and 4. So 2 times 2 times 2 times 2 times 5. I need 3 of them. So that brings a 2 out front. Third root of 10 over 4. All of these share a 2. Can I take out a 2 from all of them? Not all of them. Not this one. But I can pull a 2 out of those. And I get root 3, or third root of 10 over 2. Okay. Now let's do this problem. So the fourth root of 5 over the fourth root of 27. I have to have 4 copies of the fourth root of 27 to rationalize the denominator. Fourth root of 27, the fourth root of 27, and the fourth root of 27. Do the same thing on the top. The bottom just becomes 27. Should I multiply all those together? No. When I multiply them together, what am I going to do after that? I'm going to factor it down to its prime factorization. So I'm not even going to bother multiply them together. I'm just going to remember it's 5, 3, 3, 3, 3, 3, 3, 3, 3, 3. What do I need in order to bring something out? 4 3s. So here are 4, and here are 4. What comes out? 2 copies of 3, which makes, not 6, 9. We're multiplying. So 9 times the fourth root of, what's left? A 5 and a 3, so 15. And remember, those cannot be simplified, but this can. And they share a 9. So I get the fourth root of 15 over 3. And that cannot simplify. That's it. All right, get to work.